and continue from there. So here we have the RP equal to 1.5 du, and we have VP equal to 3 du tu. And then for the first question we have done last time. And the second question is this. Determine R2 positions and velocity V2 at a point on the orbit, which is will take 6 hours after passing point A. The point A is what we done last time, and from last time at point A, and we have the corresponding true anomaly equal to 90 degrees, and the time of flight corresponding to there, the t minus the t perigee equal to 5801.6 seconds. Okay, so based upon these informations, and we'll look at this one, we for this case we given the data t and times m is whatever the coefficients, and equal to for this one is a function of f. This is a hyperbolic. From your notes last time, this is a hyperbolic orbit. So here we are given data t. We're going to solve for f. So that means this is defined as a hard province. We have to solve for it using the numerical iterations. Okay, so that's the first concept before we come here. So now we determine data t. And so 6 hours after passing point A. So that means here we, for example, we define the data t equal to t minus t perigee. How about that? So we take the perigee as our reference. So basically here we have done is this. The travel is this. If this is the orbit, this is the perigee, and this is the point A. And from point A to current positions here, we spend another 6 hours. And from point A to perigee here, that is 5801.6 seconds. So in total, from perigee to this current point is the summation of the two times periods of time together. Okay, because here it's a little bit more convenient, we pick the perigee, because that will give us, once we do this calculation function of f, we can eliminate initial conditions here. So this one basically equal to 6 hours. Plus 5801.6 seconds. So this one we put out that one into seconds. So that is 27401.6 seconds. Okay, so right now we have data t. Then we put into calculations. So for this equation, we can implement for hyperbolic. So n equal to mu divided by minus a cubed times data t, and equal to, and that one equal to e hypersine f minus f minus e hypersine f0 minus f0. Okay, because here we pick because here we pick perigee as our starting point. So corresponding the F value there is 0. So that is the reason I pick the perigee as our reference point, because here we can eliminate this term here. Okay, this term equals 0. Okay, so we plug in all the information. So from here, A, we've been calculated last time. And what is the value of A? The value of A equal to minus 0.1305 du. Okay, and theta T, we calculated 27401.6 seconds. Okay, so therefore from here we can solve for a numerical. Okay, so that means here you just plug in whatever the functions you develop, and I think I implement this one. I think that would need about 60 iteration steps in my case. Okay, so therefore the will be equal to 4.7538 radian. So therefore here using this approach use. So from here we can solve for the corresponding true anomaly equal to 1.6337 radian. Okay, once we have that one, then the remaining will be pretty much straightforward. So we want to determine the velocity and the positions. So therefore here for positions at point 2 will be equal to P 1 plus E cosine nu. Okay, so for this case P equal to A 1 minus E squared. Okay. So now at point 2, so let me say this is the point A and this is point 2. So at point 2, and our the nu equal to, we calculated 1.6337 radian. And we've been calculated last time. And here, let me do this again. E equal to 12.5, and A equal to minus 0.1305. So from here, we can implement the R. So R for this case will be equal to 1.5 du. So this is our R2. Okay. So right now we want to determine the velocity. Velocity is where corresponding this is in parafocal corner systems. So this one comes to our formula again in our the test tube. So we know in terms of the PQW corner systems, we have such a formula here, mu over P minus sine mu, and E plus cosine nu, and 0, and PQW. Okay, and right now for this case, we have the P calculated. And P should be equal to 4.5 square, whatever. Okay. And nu equal to 1.6337 radian. So basically, we can plug in to do the calculations. So that is minus 0.063 and 3 and 0. So therefore, this is our v velocity at point 2. So therefore, v2 is the magnitude there, and that one we can approximate equal to 3 and du. So that is the solution of these questions here. The majority of these questions you're going to spend is these portions, and this portion and part pretty much go to MATLAB and then develop that programs. And here I would like to tell you, and I begin to think about the test 3, and that will be covered from all the topics beyond this point, beyond the test 2. So which means that will start from the contents of Kepler's problems, right? And right now you can see this one is pretty much is open. You have to go to have the program, numerical facilities, access to those things. So that will be the same as 2 years ago. I will reserve the SoCal, and very likely we're going to conduct the test 3, our final test in SoCal. And that means everyone will be sitting in front of your computers there and open to basically everything. Okay, and so that means that'll be the good moment. Now I think you gradually implement your numerical tools and whatever the tools, and okay. So that is for, I think using this example, I will finish the first portion of the Kepler's problems, and that is on the handouts. We have 3 sets of equations, right, for hyperbolic, for parabolic, and for elliptic orbits. And different orbit type, we have to pick up the different one. This is not saying that approach is bad, but the people hopefully want to develop a more universal method, which means one single equation fitting in all types of the orbits. Okay, and that is the second portion we're going to talk about starting from today. But anyhow, those equations, those kind of examples, right now we have been through, I think 5 or 6. They'll be good for your exercise and for your homework. So I've seen at least 1 or 2 have pretty much finished this homework. So basically take up when you have a fresh memory, and all the design of this homework this time, for the Kepler's problem, pretty much similar to those kind of examples we've been through. Okay, so take your memories and still fresh and doing the things. And my purpose of this homework assignment is to force you to develop your own code, because you can see without those codes you wouldn't be able to solve for certain problems in the homework. Okay, take a chance. Okay, so and how to develop the coding, I think I have a handout, kind of pseudocode providing to you. So that shouldn't be very hard. If you say, can I use I'm not good in MATLAB, can I use other software like Excel? I've seen 2 students before, 2 years ago, they using Excel, done a very good job, and they go to the VBA, the virtual kind of the programming. That one I don't understand. Basically, the 2 students program the Excel to do something like this one, and that is very amazing. So either way, I don't, but I can help I can help you on the MATLAB, but for other software I won't. That is, I haven't used them for a long time beyond my capacity. Okay. So this is our section. I sent email to you this morning. And right now we're going to talk about the universal formulation. And this will take time and a few lecture hours. Because of this method is so